All right, so let's look at what lab number 3 is all about. So as we have said that in this particular lab, we are using circuit simulation as a tool to understand and design circuits. And in this particular lab 3, we are going to look at circuits which consist of capacitors and inductors. And we'll look at, starting with, we'll look at RC, a resistive capacitive low pass filter. And then we'll look at a CR, a capacitance here and a resistor here, and then the voltage is taken over here. And so that's a high pass filter. And then we'll take a look at series RLC circuits and parallel RC circuits. And then finally, we'll look at how to eliminate noise from a audio signal. All right, so let's look at the microcap and go over these different parts of the lab one by one. All right, so that's so we've started our microcap simulator, and this is our low pass filter with a R of let's say 1K and a capacitance of 1 microfarad. And as we will see, note that we are taking the output here. We're taking the output here, right? Okay, so we can, although we have not called it, we can call it explicitly here V out. Okay, so that's the output here. Okay, similarly, we'll take the output for this part also there. So these are two circuits which are same, except that one of them is driven by a sinusoidal signal, and we'll do an AC analysis of this particular circuit. And this is driven by a square wave. And so we want to see transients. We want to see how the capacitor charges and discharges in this particular circuit here. So let's start with this particular circuit here. And we are saying that this is a low pass filter. That if you take the output here, what would happen is that the smaller frequencies will be able to pass through it, meaning V out will be equal to Vs1 for smaller frequencies, and higher frequencies will get rejected. Anyway, so let's see that behavior using the AC analysis here. So let's do the AC analysis, and let's remember that this particular node is V2. And by default, AC analysis, no matter what you put in this, so if you double click here, we have put 50 millivolts, 5 kilohertz and all that. So for AC analysis, it doesn't really matter. What it would do is by default, it would assume it to be 1. And frequency is something that we will sweep, okay? So let's do the AC analysis. AC here, and so this is the setup for AC analysis. So we are going to sweep the frequency from 1 megahertz, 1E6 to 10, right? So we'll observe it over this range. You can alter it if you wish, and so that is there. And the frequency is swept in logarithmically because it's a large range here. So logarithmically it is swept here, and these are the variables that we would like to plot. So note that we are plotting V2. The output voltage is V2. So we are plotting V2 as a function of frequency, and we are taking in decibels. So we are taking 20 log of V2 because that helps us to see what is the 3 dB frequency of the filter here. All right. And there are other variables that are for different parts, so don't worry about it. So let's focus on the first part here. Okay. The first part here. So let's enable this particular part here. So dB of the voltage 2, and remember the input is taking as 1 volt, so this is nothing but the gain of the circuit here. All right, so let's run. Make sure that you are an auto scale, operating point is enabled, and let's run this here. All right, so that's what we see here. So note that the lower frequencies in dB, the value is 0. 0 dB basically means gain of 1 here. And then of course, then the gain of the circuit is falling here. So what we are seeing is that frequencies up to about maybe, so let's find out the 3 dB frequency here. So the 3 dB frequency, if you want to find out, let's make it full scale here. Full scale here, let's enable the cursor. So note that the gain here is almost negligible in milli here, so very close to 0 here. So to find 3 dB frequency, we have to find a point which is 3 dB lower than this here. So let's do that. let's do that 3 dB. So it would be approximately, because this is very close to 0, so it would be minus 3 dB here. So let's go to minus 3 dB here, right here. Right, so 3 dB frequency for this particular filter is 158.876 here. And you can verify it with the formula that we have given for the 3 dB frequency, how close it matches with the expression that we have here. And we also know that for this simple filter, let's go back here. For the simple filter, this the gain here falls at 20 dB per decade here. So we can check that here. So suppose, for example, I go here and make it 1K. Go here and put it at 1K here, 1K here, and the right cursor, let's say at 10K here. Right cursor is around close to 10K here, okay? All right, so 10K, so the ratio is, we are going from 1 to 10K, and note that the change, so since we have not positioned it precisely here, the change from here to here is close to 20 dB here. And this would have been more accurate perhaps if we shift to, away from 3 dB here. So we shift to 100 here and 10K. So we are going from 10K to 100K, 10K to 100K here. And the change in delta change is 19.960. So 20 dB per decade is what this particular gain is falling. And that's because it's a first order filter here. First order filter with very simple RLC here. Right, so it's passing low frequencies and rejecting higher frequencies here. And if you wish, what you could do is you can alter, for example, if you want to change the 3 dB frequency, if you want to shift it to higher frequencies, what you could do is change it to, let's say, 0.1 here, and you can immediately see the effect here. Note that 3 dB frequency has moved right here. And so you can alter by changing the capacitance here. You can change it further, you can move it further right. So you can change 3 dB frequency either through C, or you can change it through R also, okay? So you can explore this, how you can alter the 3 dB frequency. And further, if you want to make more complicated filters, this is a first order filter, you can add another RC section here. So you have one RC followed by another RC. So that would become a second order filter, and try to see whether, whether this falls at 20 dB per decade or 40 dB per decade. And it's very easy to add a third order filter by adding three such RC sections here. All right, so that's a simple first order RC filter here. So let's look at it in the time domain. So this was in the frequency domain. So we can look at the same circuit in the time domain here. So in this case, it's the same circuit here, but we are exciting it with the square wave. So let me show you the square wave here. So where do we get this particular voltage source? Is right from here, from this source here, voltage source, right? So when you double click it, so it's a general purpose voltage source. You can specify DC, you can specify AC, and you can specify a pulse kind of a function here, right? So what we're going to do is we want to see, let's remove the AC part here. We want to look at the this thing here. We'll apply a pulse, so it's going from 0 to 5. And time delay is 0, so it will start from 0 here. This is the rise time, this is the fall time of the square wave here. The pulse width, the width of the pulse is 5 milliseconds, and it will repeat after 10 milliseconds. So it's a periodic train of pulses with a width of 5 milliseconds and repeating after 10 milliseconds. Okay, so let's see what happens here. Okay, so that's the definition of this voltage source here. And let's do transient analysis. And keep in mind, we are going to look at V3 is the output and V4 is the input here. So let's do the transient analysis. So V3, so transient analysis, we are doing it over one period, 10 millisecond. Okay, and maximum time step 0.1 microsecond is not necessary. We can make it 1 microsecond also, should work fine here. should work fine here. We should have enough resolution in the time domain to capture the waveform properly here. So all right, so these are, so what we should do is we should look at V3. So let's enable this, and V4. All right. And so in this case, I've already entered all the variables that I would like to monitor in different parts of the lab here. For you, you'll have to enter V3 here and V4 here. You'll have to create if you want to monitor these waveforms here. Again, an auto scale operating point. So let's run the simulation here. Right, so let's, this is what happens here. So let's look at so this is the circuit that we are here. Right, so this is an RC circuit here. So we apply a pulse. In blue is the input here. Blue is V4. And in red is V3. So it shows in red in V3. So we apply 0 to 5. So the capacitor starts charging, exponentially charging here. And since we have enough time, it almost charges to the final value here, 5 volt here. And then when the input goes from 5 to 0, the capacitor discharges here. All right, so that's the simple charging and discharging of the capacitor. If you wish, you can change the, if you don't want to give enough time for charging, you could reduce it to, let's say, 2 milliseconds. So let's look at what happens when we do 2 milliseconds. Right, so now it's not able to charge fully here. And of course, it has enough time to discharge, so it discharges fully here. So you can explore these things here if you wish. If you wish, what we could do is we could make it 1 millisecond, and so half a millisecond, let's say. So apply a pulse, train of pulses here, and let's run it here. Let's see what happens here. Okay, that's the interesting part, right? So we have, we have given it a very short period to charge and very short period to discharge. And this is the behavior that we get here. So we would like you to think what is really happening and why is it going in this particular manner here. All right. So let me come back to the default mode here. So this was 5 millisecond and this was 10 millisecond. All right. Okay, so in this case, the time constant is compared to the period. There's enough time for the capacitor to fully charge here, right? So that's the behavior of a simple RC circuit. If you wish, you can add more resistors and capacitors and see what is happening in the circuit. For example, let's add this here, another section here. So that's also 1K. And you can check whether it is also exponential charging or what exactly is happening here. So let's add 1 microfarad here. Let's add 1 microfarad. Let's connect it up. Let's put a ground here, right? And let's see what is happening here. So let's do the transient analysis. So note that this, if you analyze this particular waveform, it won't really be exponential because we have the exponential part is only there for a single RC circuit here, especially when we make the time constant of this particular section, let's say, different from the previous section here, right? So let's do that. So note. Anyway, so all of these things you can explore by making suitable changes in the circuits here, right? So let's go back to the previous circuit here. All right, so that's our part A, which is the RC filter here, simple RC circuit here. Now a parallel to that is what we call as the CR circuit here, right? So this is the capacitance is over here and resistance is over here, and we are taking the output here. So the difference is both are RC circuits, but the difference is the place where we are taking the output voltage here. So we are taking the output voltage here. So let's look at first the AC analysis here. So we'll look at node 6 here. And again, this is sinusoidal input, and AC analysis will take the amplitude as 1. So let's do the AC analysis here. right? So now we are going to monitor node 6 here. So let's do the node 6 here, enable this, let's run it here. Right, so now we see that this is a high pass filter here. High pass filter because lower frequencies are getting attenuated. Note that this scale is in dBs, and minus value means less than 1. 0 means value of 1, because we are taking 20 log of the output variable here. So 0 means gain of 1, and these are all attenuation here. So these lower frequencies are getting attenuated and higher frequencies are passing through. Right, as gain of 1 basically means that whatever is the voltage here, the same voltage appears over here. So that's why we call this as the high pass filter here. So here also you can determine the 3 dB frequency, and you can check the rate at which it is falling, whether it's 20 dB per decade or not. And here also you can add multiple sections of CR, and you can see how the attenuation rate changes here. Right, so you could play around with this CR circuit or a high pass filter circuit here. And you can shift the 3 dB frequency right or left by altering either the value of the resistor here or the value of the capacitor here. Right, so that's the AC part here. So looking at, so all of these circuits, you can analyze them, you can try and understand them by looking at the behavior in the frequency domain, or you could also try and understand them by looking at the behavior in the time domain here. Right, so that's what we'll do now. So let's exit the AC analysis here. And in the time domain, again, what we have done is applied note that we are applying basically a train of pulses here. 5 millisecond is the pulse width and 10 milliseconds is the period. So these pulse width and periods have been chosen so that we can clearly see the waveform, the charging, discharging, all of those things we can clearly see here. Right, and you can alter it, you can change the period, you can change the pulse width, keep the rise time and the fall time same as given here, so that we get a sharply rising and sharply falling input here, right? And we are going from 0 to 5 volt. So we'll monitor V7 is our output and V8 is the input here. So let's do the transient analysis, V7 and V8. So let's remove this. So let's enable V7 and V8 here, right? And let's run auto scale, and all of that is there here. All right, so that's what happens here. So we can see the circuit and this simultaneously here. And this is how the circuit is behaving here. So when we apply a pulse here, so in blue is you go from 0 to 5. The capacitor instantaneously, of course, capacitor acts as a short, so the same voltage appears across the resistor here. So the output immediately goes to 5 volt here, but then the capacitor starts charging, and so the amount of voltage that is available on the resistor decreases here and eventually falls to 0 here, right? And something similar happens on the negative side here. So, like the previous circuit, RC circuit is more like an integrator. This circuit is more like a differentiator, not a perfect differentiator, but you are seeing that by when you're applying a pulse, it's like differentiating this particular voltage here, right? And the differentiation would become even better. You would get a very sharp pulse if we make the time constants very small here. So for example, if we make 0.1, so note that this thing, and if you make it 0.01, right, so it will be like almost like a, so there's a impulse here and there's an impulse here. So wherever there is a change, there is a value of the output here, when it's differentiating, and wherever there's a change here, so because the change is from 5 to 0 here, so there's a negative impulse here. Anyway, so you can study these things in the time domain also. Again, you can add more CR sections, you can add more CR sections here, and you can explore. You can explore what the, note that when we did these circuits in ESC201, a simple CR circuit is easy to analyze, but if we add 2 sections of CR, when you have 2 capacitors and 2 resistors, or 3 capacitors and 3 resistors, then the analytical solution becomes more difficult. And that's where simulation becomes a powerful tool to understand what really happens when we add a series of CR sections, okay? A series of CR sections here and here. All right, so that's for exploring a simple RC circuit as a low pass filter and as a high pass filter. All right. The next thing that we look at is series RLC. Right, so this is part B here. So this, as all of you recognize, again we will look at them in the frequency domain, and we'll look at them in the time domain here. Right, so you will recognize a series RLC circuit, and it's a resonance circuit, and it has a Q factor here. Q factor defined as omega naught, which is the resonant frequency, center frequency, omega naught L by R. And depending on the value of Q, we have different kind of responses. And so let's look at it. So first in the frequency domain, so we'll look at output V11. So let's do that analysis, AC, V11. So let's remove it here, V11. Let's enable this here. All right. Okay, so output here, V11, what you see here is, it's also a low pass filter here. It passes lower frequencies and it attenuates higher frequencies. In between, at resonant frequency, there is a higher gain here. So at resonance, if you would recall, what would happen is that the reactance due to inductance and capacitance, they cancel each other. So we have a large current going here. And this large current flowing through this capacitor then results in a larger voltage here. Anyway, so the theory part you've already done, and you can refresh by going over the lectures once more. And here is where we can explore how this particular circuit behaves here. Now this is the voltage across the capacitor. If you wish, you can look at the voltage across the resistor here, or you could look at the voltage across the the inductor here and the resistor here, or you could look at the currents. You could look at any of those variables. For example, if we want to look at the voltage across the inductor, so we go here, AC, limits, and voltage across the inductor will be node 11 minus node 10. So we go here, node 11, and we add minus V10 here. Right, so that will give us and run it again. So note that the voltage across the inductor is like a high pass filter. Okay, so this is like a high pass filter here. And you can monitor the voltage across the resistor here. You would see that it's like a band pass filter here. All right, so across this is a low pass filter, across this is a high pass filter, and across this is a band pass filter. If you wish, you can monitor the rate at which it is falling. All right, so for example, again, go back to here. So for we can look at 10 hertz, 10 hertz, and then we can look at 100 hertz here, right? So 1 decade. So note that when we go from 100 to 10, you're right, so the frequency is almost like 1 decade, and the change is about 40. Change is 40, so this falls at 40 dB per decade here. 40 dBs per decade, and that's happening because this is a second order filter here. So second order filter, so when you write the transfer function, or you get omega square in the denominator, and similarly when you write down the differential equation, you get a second order differential equation here. So it's a second order filter, and what you can measure is the Q factor here. So Q factor, if you wish to measure, you have to focus on this particular part here. So the Q factor is basically, experimentally, if you want to measure here, it is equal to the center frequency, and F2 minus F1 are the 3 dB frequencies here. So let's zoom to this region here and try and measure. So you could do that. So we could, to focus on this particular part, we can just simulate from, let's say, 1K to 10K, all right? So we can change this from 1K to 10K. So 10K is 1E4 and 1K is 1E3, right? So we can focus on that. Okay, so now it's better. If you want to find out where the center frequency is, just use this peak value, it will find out for you. So the center frequency is 2.265, so that's F0. And you want to find out where the 3 dB frequency is, then note that this is 17 dBs here. This is 17 dBs here, so 3 dB frequency would be 3 dBs lower here, so you have to find a point which is 14 dB here. So let's look at 14 dB here. Right, so this is here, 14 dBs at 2.44. So this is F0, this is equal to F2. If you want to find out where is F1, so there's another 3 dB frequency here. So let's go on this side here. 14, we have to go to 14 here, right? Approximately, we have to position it properly. Right here, 2.118. So you know then all these frequencies here, you know F0, the center frequency, and you know the two 3 dB frequencies here, one above F0 and one below F0 here. And then you can use this expression to calculate, to measure Q factor here. And then you have a formula for Q factor and you can compare the two here, right? You can do both of those things here. All right, so we can go back to our limits here, AC1E6 and 1E2 here, all right? So 1E1 here, okay? We can go back to this here. And if you want to increase the Q, it's obvious how to do it. One way is you reduce R. See, we can see what happens here, right? So 10. So note that this particular part of the curve becomes sharper here. Note that F0 by if F2 minus F1, F0 will basically depend on L and C. F0 is equal to 1 over 2 pi square root LC here. So as long as you don't touch L and C here, the center frequency remains the same. And you get a higher Q factor because F2 minus F1 becomes smaller and smaller here. So this graph becomes sharper here. Okay. So that's the behavior. You can study this resonant frequency, the series resonance circuit in the frequency domain in this manner here. If you wish, you can also look at the phase here. You can look at the phase. You can look at the magnitude at any point in dBs, and you can look at the phase at any point with respect to frequency here. So that's the series RLC circuit in the frequency domain. So let's come out of the AC part here, and then what we'll do is we'll look at this part of the circuit in transient domain here. So in transient domain, again, we have done the same thing. Same 5 millivolt pulse width, and period is 10 millivolt here, so everything is the same here. So let's run the transient analysis here. So now note that we are monitoring for transient analysis. For transient analysis, we need to monitor V14 and V13, right? So let's go back here, V14 and V13. So disable these ones, V14 and V13. So let's enable this here and let's run it here. Right, so this is what you get here. Okay, so the moment you apply a pulse here, so what happens is the capacitor has to charge, but because of this resonance here, you get these oscillations here. And gradually the voltage across the capacitor settles down to the value which is expected. We know that if this is 5 volt here, eventually no current is flowing and the voltage across the capacitor will be 5 volts. So that's where it is here. But the moment you switch from here, this again starts to vary here, right? So you see this, it doesn't, discharge exponentially here, but it exhibits oscillations. That's because we have Q greater than 0.5 here, right? So, and we can alter the Q here. So for example, if we make R higher here, so we can see what happens here. So note that we get very little oscillation here, right? So it just charges up and then discharges here. Even this can disappear completely. Now you see more or less, you don't see much effect of resonance because it's basically the resistor which is dominating here. So it looks more like a normal exponential charging and discharging here, right? So because Q is very, very small here. So effects of resonance are not much seen here. So you can go back here and you can see these. So when it is 10, there are very strong effects of resonance here. You don't see, so the oscillations take a lot more time to die down. And this 5 millisecond is not enough for output to settle down here, right? So note that these are the things that you would expect whenever you have a second order system or a higher order systems here. When you suddenly apply a pulse to a higher order system here, more than with order more than 1, and if Q factor is greater than 0.5, you expect all these oscillations to occur. So note that there's an overshoot. The final value is 5 volt, but there's an overshoot and there's an undershoot, and it takes a certain amount of time for the output to settle down. Similarly, it takes a certain amount of time for the output to settle down when we switch it back to 0 here. Right, so this is a common phenomena that we see in many of the systems, higher order systems, whenever we apply a pulse here, especially if Q is larger than 1. And the more the Q factor here, the more time it takes to settle down, right? And so all of these things you can explore through simulation very easily. You can alter any of these values and you can see what happens here. So that's a series RLC circuit, right? And something similar, complementary part is the parallel RC circuit here, right? So this is the parallel RC circuit. All right, so this again, as we said, we'll explore it in the frequency domain, and we'll explore it in the time domain here. So the node to monitor is V16. So let's do the AC analysis here. V16 here. Let's disable this and enable V16 here in dBs. Right. So we see so this particular filter that you can see here when I'm taking the output here acts like a bandpass filter here. It attenuates both the lower frequencies and attenuates both the higher frequencies here. And again, you can calculate what the Q factor is by finding the center frequency, then finding an upper 3 dB frequency and a lower 3 dB frequency, and then using the expression that we have here. Right? Q is equal to F0 F2 minus F1 here. And you can make the resonance sharper. This, for example, if you would like to pass one particular frequency, let's say, and attenuate all the others, you need to make the curve sharper here. So we could do that by increasing the value here. This is 10 ohms here, so let's do 100 here. We have to run the here again. Okay, so let's see. All right, so let's see here. Let's run here. Okay, so this is let's see here. So let's keep this as a this was, so I was changing the name of R10 rather than changing the resistor here, so that's why. So let's change the resistor here. Let's put it to 10K here. All right, so we can see it becoming sharper here, right? And so note that the Q factor is higher, and now it's rejecting the other frequencies far more as compared to the center frequency here. So we can make it even sharper here by increasing to 100K here. Right, so now it will just pass the center frequency, and all other frequencies that you see here, they're getting sharply attenuated here. Right, so you can measure the Q, and depending on the kind of attenuation that you want over the other frequencies, you can then decide on what value of Q is suitable for you here. Right? So even here. So anyway, so these are the things that you can explore through simulation here, right? So impact of Q on, and if you would like to alter the center frequency, of course, you can do it through LNC here. You can shift it right and you can shift it left here, and you can alter the Q factor through this 1K here, right? So that's the parallel RLC circuit here, and in the frequency domain. And the same thing, then we can look at it, what happens in the time domain here. So in the time domain, you monitor V17 and V18 here. So let's do the transient simulation, and let's enable here V17 and V18 here, and let's look at them, right? So this is what happens here. So we apply a sudden pulse here, input here. This is the input from 0 to 5 and back to 0 here. And this is the output here. So note that the final value of the here, so when you apply a pulse here, the final value of the output voltage will have to be 0 here, because note that once we reach steady state, then the voltage across the the current across the inductor is no longer changing with time, and therefore the output voltage is 0 here, right? So that's where is there. But because of the resonance here, the output rises and then oscillates and then goes to eventually 0 here. We could decrease the Q factor here. Note that it doesn't oscillate and then it rises and then it goes back to 0 here, right? So it goes back like that here. So depending on the Q factor here, the behavior of the circuit, of course, changes. Whether there are oscillations or not, it all depends on whether Q is greater than or less than 0.5 here. And so again, you can explore the effects of this particular circuit here. We can go back to say 1 microsecond here. So note that when we change 1 microsecond, again there are oscillations here, and go back to 0.1K here. So you can try all of these things here. So note that it rises and then exponentially goes down here, right? So all of these things you can explore and understand both these series RLC and parallel RLC circuits, and the simple low-pass filters and high-pass filters. You can get a much better appreciation by exploring these circuits and using this particular tool, simulation tool here. All right, so let's come out of that. And finally, as a last part of the problem here, so as after studying the simple RC filters and RLC filters, what we have here is a audio signal here. And so this is the audio signal here. So this particular simulator allows you to add an input, which is a audio signal in this audio format here. It's called the WAV file format here, right? So, and you can choose any song or any tune or whatever you like. Once you have it in this particular audio file format, then you can create an input by reading that particular file here, specifying the path of the file here, and you will get that. You can create an input corresponding to that particular one. So this is what I've done here. One particular song which was there in this particular audio file format. So this is the input here. And what I've done is added in series to it a sinusoid of 0.1 at 1 kilohertz. So this is like what I'm trying to do is I've corrupted this particular song by adding a 1 kilohertz tone there, single tone there, right? And so at node 1, we have the sum of the song plus a 1 kilohertz sinusoid here. And what I would like you to do is create a filter which will remove this particular 1 kilohertz signal from here so that you can listen to the song properly here. So in this case, I've just put a simple RC filter. This is not going to work. You have to create some other kind of a filter, maybe an RLC, maybe you have to think of what to do in order to remove. So you have to create a filter here such that at the output, you can listen to this particular song free of the sinusoid here. So let me illustrate. So for example, let me show you how this song corrupted by this 1 kilohertz tone sounds like here. Okay, so what I'm going to do is do a transient simulation here. Okay, so analysis. By the way, this scale here, the scale has been set to 1. Okay, so you can increase or decrease the amplitude of this particular audio signal by adjusting the scale here. And the sinusoidal input here, notice 0.1 volt and 1 kilohertz. Okay, all right. So you could take any particular song or any particular tune and add a 1 kilohertz sinusoidal signal, and thereby you'll get a noisy, a corrupted audio signal here, and you have to create a filter so as to remove the effect of this particular sinusoid. Okay, so let's do a transient simulation. So we're going to look at node voltage V1, okay, which is the sum of this, and you can see that the sum is corrupted. If you listen carefully, you can see that the sum is corrupted. So we are looking at V1 here, and the harmonics, you can see what are the harmonics present in V1, so we'll not bother about it. I'm simulating for 20 seconds with a maximum time step of 0.1 millisecond auto scale, and so let's run it here. Let's run the simulation and see the waveform. So it will take some time because I'm running it for 20 seconds here, and there are lots of high frequency components. So this is my audio signal, corrupted audio signal, corrupted by 1 kilohertz sinusoid. So it will take some time for simulation to occur. Well, to listen to this particular song, at least we need a couple of seconds. 20 seconds may allow us to listen to it. All right, so let's see. So here, of course, is a signal here. You can't see a 1 kilohertz sinusoid or anything, so very difficult to see in the time domain. All right, so it says let's cancel. So this, so it has given me the output V1 is the sum of the song and the sinusoid, right? So if you double click on it, you get this window here, and there are lots of things here, but it says save curve. All right, so go into that save curve here. It's already the save curve here, so you see this here. And if you select V1, then what you can do is you can play the audio signal here, right, and do an auto range here, and you can play. So you can listen to how the corrupted song sounds like, and then when you filter it, you can see whether the the effects of the corruption has been removed or not. That 1 kilohertz sinusoid has been removed or not. So let me play it, and you can, if you listen carefully, I'm sure you can hear the 1 kilohertz tone along with the song here. All right, so that was 20 seconds of that particular song. So now your goal is to, let me remove it. Your goal is to go back here and create a suitable filter here. Suitable RC, RLC, whatever you think will remove this particular sinusoid. And then you can listen to the song again and enjoy it again. All right, so that's the fun part of this particular lab. And also you learn, how to use some of those things that we just learned in order to create a suitable filter. Now, the solution will not be a simple RC, a simple CR, or series RLC. You'll have to think about how to remove that particular tone here, right? So you can take any particular song of your choice and add a sinusoid to it and create that corrupted signal here, right? So so make it 1 kilohertz with an amplitude of 0.1 volt, and any song of your choice in that audio file format here. And then you can play around with this filtering here. And besides trying to remove the effects of this sinusoid here, you could just take the song and you could create a low pass filter, you could create a high pass filter, you could create a band pass, and you can see what effect it has on the quality of the song. All right, the kind of audio that you get here. So you can play around and have some fun with the simulation here. All right, so let's stop here.